In order to highlight the energy possessed by electron in an atom, we usually represent the orbit's location according to the energy or relative distance from the nucleus. These are called energy levels. Note that each level can hold only limited number of electrons, and the available energy states unfilled by electron are indicated by empty space here. When atoms are put together, they share the spaces of the outermost orbits by taking electrons from the neighboring atoms to fill the empty space in the outermost orbits. This forms covalent bonds as described in chemistry. A silicon atom forms bonds with 4 neighboring atoms, and all the energy states in the third orbit are then occupied by electrons. But there are other higher energy levels with empty spaces, which are not shown in the picture. To look at the details of electron interactions, we magnify the position of electrons around a few atoms. Just a reminder that the drawing here are only simplified representations with many quantum mechanics concepts being skipped. But it is important to have a good understanding of the overall picture first before going to the fine details. In fact, the picture presented here is sufficient even for the experts to communicate and exchange ideas. When atoms share the outermost orbit that contains electrons, each atom retains its electrons at the lower energy orbits and not sharing with other atoms. That means electrons in the inner core orbits cannot move to other atoms. When atoms are put together, the orbits at the same energy level are combined to form energy bands across the entire crystal. When forming an energy band, the orbits split, indicating that electrons can stay at a wider range of energies instead of just one particular level. The energy band where electrons are shared is called the valence band. In the valence band, all the spaces that can hold electrons are filled by electrons. The first empty band just above the valence band is called the conduction band. In the conduction band, there are spaces for electrons, but they are almost empty. That is, there is almost no electron in the conduction band. Between the valence band and the conduction band, there is a band gap where there is no space for electrons. Sometimes it is also called the forbidden gap, as no electrons can stay at energy located in the band gap. The focus in the study of semiconductors is the carrier actions taking place in the valence band and the conduction band of a crystal. In the valence band, the electrons cannot move as there is no space for them to move to. In the conduction band, there is almost no electron to move around. Therefore, there is almost no electrical conductions in this crystal. At room temperature, some energy is applied to the system so that some electrons gain enough energy to get excited from the valence band to the conduction band. Once an electron is in the conduction band, it can move around freely as there are many spaces for it to move to. In the valence band, an empty space is left behind, which we call a hole. Let me remind you that an atom, which consists of a positively charged nucleus surrounded by negatively charged electrons, is electrically neutral. When an electron is excited to the conduction band and moves away, there is an excess positive charge left at the atom core where the hole is located. So holes are often referred to as carriers of positive charges. To be more exact, holes are associated with positive charges where they are located. But for convenience, we will just assume holes carry positive charges.